Okay, we have today 8M3 lesson 2, properties of dilations. Now, we have talked about, and 8M2 had a lot of work, a lot of learning, a lot of teaching on translations, reflections, and rotations, which are all transformations. They're all rigid transformations. Recall that we could take a triangle and we could translate it, we could rotate it, or we could reflect it, and those were all rigid transformations, and there were properties of those three types of transformations. They were, regardless of which of those three you chose, they would always maintain your segment length and angle measure. Now, what we're going to do today is we're going to learn a little bit about the properties of what we started on yesterday, the properties of dilations, which all are similar, no pun intended, for those of you caught that joke, but they, but not exactly the same properties of that occur for rigid transformations. Remember, dilations are transformations of objects where we maintain the shape, but not necessarily the size. So let's talk about what those properties of those objects are, and then we will talk about, we will do some examples of how we can perform those dilations. We did a little bit of that yesterday, and then we're going to go into some homework help. Okay, so here we are. We're going to talk about, again, properties of dilation. So here's the whole key to today's lesson. So dilations, remember dilations, whoops, let's go and turn our pencil on. Dilations, they are like rigid transformations in that they map lines to lines. They map rays to rays, and they map segments to line segments, or just segments to segments. These are also line segments. Now, and we're going to focus on, this is going to be our focus here, because if you map if a dilation maps a segment to a segment, then it also, you can say it maps polygons to polygons. And why is that? Because if if a dilation turns one, sorry, if it takes a segment and it maps it to another segment, then it can take, let's see, if we can if it maps, if you take, PQ and map it to P prime, P prime, Q prime through a dilation, right? This would be a growth. Then by definition, it could map a triangle, if those were the same size. If this was P, Q, R, it could map it to P prime, Q prime, and R prime, because polygons are simply, three or more line segments, right? Okay, again, so they map lines to lines, rays to rays, and segments to segments, by growing them or shrinking them. Now that's the key difference between this and rigid rigid transformations. But so these are not necessarily, well, these are not necessarily the same size. right? And so that, again, in rigid transformations, these are the same size. But in dilations, as you can see here in my two examples, PQ and P prime Q prime are not the same size, and neither are PQR and P prime Q prime R prime. Same shape, different size. Now the final piece, the final rule, and let's see if we can find the same color here. I think we're kind of in this kind of reddish zone. Well, I can't find that color here. Maybe it's this color. D is it maps angles to angles, and the angles do have the same measure, and we'll see that. Okay, so while the line segments don't necessarily have to be the same size, the angles are the same size. It doesn't matter how, if you have a triangle that's the same shape as another triangle and you blow it up or you shrink it down, all of the angles will maintain the same size. So these are your 4 key rules of dilations, your 4 key rules. Or at least the 4 key rules as it's outlined in our manual. So let's talk now, and we talked in lesson 1 about dilation and how you do it. I'm going to show you again how you do it, and then we're going to go, and I'm going to do it on a sketch pad. And now on Sketchpad, I don't have a ruler, but I'm going to expect you to do a ruler. I'm going to talk you through what I want you to do as I kind of show it to you on the sketch pad, this being the sketch pad. And then we're going to go do it in GeoGebra, and I'm going to show you how to perform some dilations on various objects using different dilation factors, different scale factors, and it will be similar to the homework that you have for tonight. So let's open up. ADEM 3, lesson 2. Let's talk about dilation. So here's going to be an example of dilation with scale factor greater than 1. Here, let me write that out. Greater than 1. Greater than 1. Now, when I say greater than 1, what does that mean? That should tell you something. That means we are what? Growing or shrinking? Right, that means we are growing the object. We are growing this object. Example of dilation with scale factor greater than 1, growing. Remember, 1 equals same size, scale factor. 1 is same size, less than 1 is shrink, greater than 1 is grow. Let's not forget that. And you'll see why as we walk through this example. So whenever we do a dilation needs an object we are acting on, we are growing, well, let's just say we're acting on. It needs like an origin or point of dilation. That's the point that we're growing or shrinking from. And C, we need a scale factor. Okay, so that's when we talk about dilations, you got to be talking about all 3 of these things. So let's do the simplest case, and we're going to do just a, here, let's start over here. We're going to do just a triangle. Okay, so that's our object. right? Our object. And we're just going to call this, we got side A, B, C. Okay, that's point B, and that's point C. Now we have a point. Now we need our origin, or our point of dilation. So let's put that point right here. Yeah, let's leave that in orange. We'll call this. This is kind of our starting point. Point O. And now we need a scale factor. So let's blow this thing up. Let's do it 1.5 times. So we're not doubling. It's growing it because it's greater than 1, but we're not doubling the size. We're just going to make it 1.5 times bigger. Now, the way that we do it is the same way that we did a lot of other things, a lot of other transformations. We're going to we're going to look at each point. We're going to act on each point on this object. And we're going to dilate. We're going to dilate each one, and then we're going to draw our final object. Okay, so I'm going to kind of get these things out of the way. A, B, and C. Let me just delete them here. So that I can, you'll see why I'm doing that, because I have to perform this dilation. So we are going to take our array, and we're going to go from here to here, and that's our original ray. Right? So we're going to dilate about this point here, OA. This is a ray, OA, and we have to make it 1.5 times bigger. So that's this size plus another half. So 1.5 times this length. And so we're going to add, again, we're going to add another half. So we're going to do that like this. That would be doubling. So we're just going to go about 1.5 times. And you're going to use a ruler. So it's going to be a lot easier than what I'm doing, because I can't use a ruler on this surface here. So I'm just going to make it about 1.5 times longer. See, that's about 1.5 times longer. And so I'm going to draw my new point. We have this whole problem again where the thing's disappearing on us. And again, this isn't perfect. So now I'm going to draw my new point, and I'm going to draw it in, let's draw it in light blue. Okay. So I've dilated that point. I've made it about 1.5 times longer. Again, if you had a ruler, you'd just measure halfway along here to here, and then you'd extend it out across that same line segment to here. So now let's make this point here. So we're going to make this 1.5 times. Whoops, don't move it. Leave it there. Make it 1.5 times longer. And we're going to draw our new point here. Okay, see how we're doing this? Now we're going to make our last ray. And again, you're going to do a much better job than I am. Because you are going to use a ruler. So you're going to make a line that's about 1.5 times longer. And then make a point out here. So let's see how we did here. So we're going to get rid of our that thing. So now we have let's go back and relabel our points. So we had, let's label them really neatly. See exactly what we did here. So here we had A, B, C, and then we had A prime, B prime, and C prime. And now let's finish off our triangle, and let's draw it in. And so we have dilated this triangle. Now notice, let's look at the properties of our triangle. Each segment, we have a segment. So let's go back. Let's just remind ourselves real quick here. What are our rules? We map line to line, rays to rays. We don't have a line or a ray, but we map segments to segments, and then we map angles to angles. Our segments are not necessarily the same size, but our angles do have the same measure. So let's take a look at that. Let's make sure our properties are true. So we map, whoops, we don't want that. We want to say that we mapped segments to segments. You know, the not necessarily same size. That's A. And then B, that we map angles to angles, and they are the same measure. Okay, so let's look at our two cases here. So we have AB. So let's just draw this in. So we have AB here, right? And we have an A prime, B prime here. So those map. A prime, B prime. So our segments do map. We have a B, C here and a B prime, C prime here. And then we have a AC here and an A prime, C prime here. So this says that our segments map, check. You know, and we can just give ourselves, you know, let's just give ourselves a little happy cat here. So now we talk about our angles are the same. We map angles to angles, and that is the case. We'll just draw this straight on here. Watch this. A to A, angle B to angle B prime, and angle C to angle C prime. And they're the same size. If you took out a protractor, you should be able to see that that's a right angle and that that's a right angle. These angles are probably about, this is probably about 40 degrees. And that's about 40 degrees. And this one's probably about 50 degrees. And those are the same size. We're going to mark that with two lines. So these have two lines, one line, and a right angle. And then each one of these sides is not the same size as this one, but it's a 1.5 times bigger. So if you took out a ruler and you measured these, they should be about 1.5 times bigger. Again, I didn't use this using a perfect ruler. I just kind of estimated it using the best tools I had on this drawing pad, but you can kind of see that this should be about 1.5 times bigger each side. Okay, so I've showed you. So what else did we do here? You know, I showed you. You learned how to dilate. You know, you learned how to dilate. That's key. You dilate, and the key is to dilate one vertex at a time. And again, we'll happy cat that. You learned how to dilate. So if you have a triangle, you're going to dilate 3 points. If you had a square or a rectangle, you'd dilate 4 points. If you had a pentagon, a 5-sided object, you dilate 5 points, and then draw in your you draw in your shape at the end. You draw in your line segments at the end. Okay, now let's move on, and we're going to move into homework help, in which case I'm going to use GeoGebra, but you probably aren't using GeoGebra on your homework. You're probably doing it on paper, and you're probably doing it with a ruler and a straight edge. But I'm going to kind of talk you through this and make sure that you understand how you will be doing this as you watch me do it. on GeoGebra. So what we're going to do first is we're going to dilate. Well, let's do it with a pen. We're going to dilate a triangle. Okay, we're going to dilate a triangle and we're going to shrink it. So think about that. If we shrink it, that means our scale factor is what? Think about it. If you're paying attention, you should remember that if you're shrinking something, your R factor is going to be less than 1. Right? 1 is 1 times the size. It is the same size. If it's greater than 1, you're blowing it up 2 times, 3 times, 1.5 times. If you're shrinking it, R is less than 1. So we are going to, remember we need 3 things. We need an object. Our object is a triangle. Triangle. Our point is going to be the origin. And our R factor is going to be shrinking, and we're going to choose R factor of equal to 1/4. Okay, so let's draw our triangle. We could draw this thing anywhere, but let's draw it right here. Let's say, let's do an obtuse triangle, one like this. And we're going to shrink it by 1/4. So what we're going to do is you're going to draw a line. You're going to draw a line segment from your point of dilation up to each vertex. Right? And what you're going to do is you want to make a point that's 1/4, because our R is 1/4. So we're going to make a point that's 1/4 of the way along this line segment. So if you measure this and this is 8, you are going to make a point that's 2 along this line. Now I can kind of cheat because I got this tool here that allows me, I'm going to do it like this. I'm going to type it in. I want to dilate along point A. Oops, let's see, dilate A 0.25, comma O. And so I have built A prime. So in an imaginary world, I've placed A prime 1/4 of the way along here. Again, you're going to have to use a ruler and measure this measure this distance from O to A. You know, you're going to measure the distance from O to A and divide by 4. Right? And then you're going to put that point right there. Okay? Similarly, you're going to do that with B. So I'm going to do it my way. Dilate point B 0.25 about point O. And so I have made this point here is 1/4 of the way along this ray from O to B. Now from O to C, I'm going to take another point and I'm going to make it 1/4 of the way along there. So I'm going to use my dilation command. Again, you're going to use a ruler, and you have made each of these points now 1/4 of the way along those rays. Now I'm going to draw in my polygon or my triangle, which is a polygon, and I have a shape that is, whoops, let's move, let's take this, and let's just, because we can, polygon, make it orange. Kind of cool. Okay, so I have dilated a triangle using a factor of one, scale factor of a fourth about the origin. And that's cool. So now what is true about each one? Let's remember what is true about these line segments. Let's write that in, and let's just write it in freehand. One, the segments are mapped, right? We have AB to A prime, B prime, AC to A prime, C prime, and BC to B prime, C prime. And but they're different lengths. They're 1/4 the length, right? Because we have an object that's 1/4, each side is 1/4 the length. But the angles whoa, that's just ridiculous. Oh my goodness. It just undid oh my goodness. It undid everything. Oh my goodness. Well, let's just go through. I'm just going to dilate everything. I'm going to type in my commands really quickly. Dilate. Okay, and now I'm going to draw on my triangle. Okay, and so now I have my dilated triangle again. And what I was going to say is that each one of these angles, angle A, angle A and angle A prime are the same measure, as are angle B and angle B prime and angle C and angle C prime. These are all the same measure. Okay, and you can look at it and you can kind of see that. Now what I'm going to do is I want to dilate. We're going to dilate a different, we're just going to leave this screen and we're going to refresh it. Whoops. New. Let's make a new one. New. Okay, here we go. Let's move this down. We're going to have a point. We're going to dilate around the origin again. We're going to call it point O. Okay, now what we're going to do is we're going to do another dilation, and we're going to grow it. We're going to dilate and grow. And this is your homework help. And we're going to choose a random object like a let's see here. So let's take an object like that. And what we're going to do is we're going to take that object and we're going to grow it. We're going to make it an R of 3. So we're going to, so R equals 3. We're going to dilate it. So my questions for you are, and I want you to do this on your own. So you can just draw an object. It's kind of like this one on your graph paper. Just draw one and it doesn't have to be exactly the same size, but notice how it goes down and it kind of comes in on itself, and then it goes back out. Draw something like this and dilate it. Now the questions are this: are A, are new angles, in the new object the same measure as original object? And you can answer that before you even do it. And B is to perform the dilation. And C is how much bigger is each segment than original segment. Now, I want you to now I want you to pause plus answer plus try. Okay, I assume you're back now. So now that we are back and you've answered this question and you've done the dilation, let's see how you did. Now the question, are the new angles in the new object the same measure as the original object? And the answer is the answer is yes. Because dilations preserve angle measures. Okay, now we have to perform the dilation. Now the way that we do that, remember, is we're going to make lines that go from we're going to dilate each point. So we're going to need to perform 4 dilations, 1 for each point, and then we're going to draw in our final piece. So we're going to make a line that goes, O to B, or we can just make it, let's just make them rays because that's technically what we're supposed to do. So let's make these rays. And we're going to measure 3 times along, because R is 3, we're going to go out 3 times. So if we measure this and this becomes 2.5, we'd have to multiply that by 2.5 and go 2 more distances out here to get 3 times the length. So I'm going to use my handy dandy kind of fake ruler here, and I'm going to make a point that is 3 times out from here, right? So if this is OB, this one here is 3 times longer. B prime is 3 times further away from O than B. We're going to do the same thing for point A. Okay, so again, this is O to A prime is 3 times as far as from O to A. You're going to use your ruler and take this distance, multiply it by 3, and then go this distance. We're going to do the same thing with point D. And then we're going to do the same thing with point C. And here's point C down here. Now we're going to make our new shape, and you're going to see that our new shape, if we've done everything correctly, should be the same shape but different size. So let's go from A to B to C to D. And notice, we have the same, we do indeed have the same shape. It's just a different size. All the angles should be the same. If you measure measure angle B and B prime, they should be the same. If you measure A and A prime, same size. Same with angle D prime and C prime. Now, my final question, C, was how much bigger is each segment than the original segment? Well, the answer to that, for those of you getting A pluses, is it should be 3 times bigger. 3 times bigger. Each segment is 3 times bigger. So if you measure from A to B, it is 3 times, A prime, B prime is 3 times further. Similarly, if you measure the distance from B to C, it is B prime to C prime is 3 times longer than BC. And the same for each segment along the way. Okay, hopefully this was so you're going to have some questions. I think 4 and 5 on your homework are going to ask you about angle measures of dilations and segment sizes and dilations. And hopefully you know the answer. This problem right here answered that question for you, in addition to showing you how to perform dilations yourself. So hopefully this was a useful exercise. Hopefully you had fun doing dilations. I think dilations are a lot of fun to perform. It's kind of cool how you just take each point and dilate each point and then connect the points at the end, and magically you have an object that's exactly the same shape but a different size than you started. We're going to build on this in the next unit, and we're going to start looking at, or in the next lesson, and we're going to be looking at curved objects and dilating those, and things become even more fascinating. So, thank you. I do it because you care. All right. See you next time.